Today we are talking about differential calculus. Differential calculus is the rate of change, the rate at which things change. So, for example, the speed of a car is the rate at which the distance it travels changes with time. So first we're going to look at the gradient of a straight line and how that works with rate of change, and then we'll look at the gradient of a curved line with respect to rate of change. So we know the gradient of a straight line is the change in y over the change in x, or y2 minus y1 over x2 minus x1. So m is our fixed constant, and we have the gradient can be thought of as the rate of change of y with respect to x. A curve is a little different than that. A curve doesn't have any constant gradient. It's changing all the time. So the gradient or the slope is going to change all the time as well. So what we're going to try and do is we're going to try and find the gradient at any specific point on the curve, and that is called the tangent to the curve. The tangent to the curve. So what that means is that is where this thing touches the graph at one point and one point only. And we'll look at that a little bit more here in a second. Alright, so a tangent line touches the curve, but it does not cut the curve. We often say that it's perpendicular to the curve. If you notice though, we can't quite find the gradient of that line because we only have one point. And as we just looked, when we are trying to find the gradient of a line, of any straight line, we need 2 points. So we're going to look at what we'll do is we'll take a second line and we'll find out what the slope of that is, or the gradient of that line, a to b1. But that's not going to quite get us the same slope as the tangent line. We can see that these things are different. This is different than this. You can see they're clearly going to be different angles, so they're going to have different slopes. So we can try finding another line that's a little bit closer. So here we've got a to b2. That's getting a little bit closer to the tangent line, but it's not quite the same still. Or we could get closer still, but we're still not quite there. So what we're going to do is we're going to keep on getting closer and closer and closer to point A without it actually becoming point A. And if this sounds like a limit, you're exactly right. We're going to be using limits with this idea. The whole basis is kind of based on limits. But we'll look at some practical examples first. Okay, so let's look at it with some numbers. So here we've got 2 points. We're looking at the graph of y equals x squared, and we've got our domain restriction here, but we're not as concerned about that right now. But we just know that we're looking at this line from A to B, and we want to find the gradient of the curve at A. So we want to find the gradient of the point right here. So how do we go about doing that? Well, we're going to find the gradient is 5 for the line AB1. Alright, but that's not quite finding the gradient at point A. So let's see if we can get ourselves closer and closer. So first thing, we're going to look at the changes of x and how they change to y. So here we're going from 2 to 3 for our x, and then our y changes from 4 to 9, right? So we'll just finish, we'll fill in our table here, and we get our gradient of 5. So let's look at another line as we get a little bit closer. We're a little bit closer to point A. So we'll go from 2 to 2.5 instead. Let's cut this distance in half. So we're going 2 to 2.5. Our y value, remember we're looking at y equals x squared, so we're going to square our x. 2.5 squared is 6.25. We're going to find the the change there from 4 to 6.25, and our slope is 4.5. Move a little bit closer. How about 2 to 2.1? So we've got an even closer line. Again, 4.41 is 2.1 squared. You can calculate that and maybe even pause for a second and calculate these values as we get closer and closer. So we're getting closer to A with each subsequent B1, B1, B2, B3, B4. We're getting closer to A until we can get to the actual tangent of that. Pause the video for a second and fill out the table and see what you get. Okay, so you should have seen as you move closer and closer and finding your gradient, we are getting closer to 4. So this suggests that we're getting closer, that the gradient of the curve at y equals x squared at the point 2, 4 is going to be 4. So the slope at that point, at the point 2, 4, is going to be 4. And if we look at our graph here, looking at our tangent line, here we are roughly moving one spot from x, from our one spot here, and then we move up 1, 2, 3, 4 spots. So we've got our gradient of 1 and 4. So we've got the change in x, the change in y over the change in x. So we have our slope as being 4 over 1, or 4. Okay, so let's look at another example. We're going to find the gradient of a chord joining 2 points between 1 and 1.001. We're going to try and find the gradient, or make a guess about what that's going to be at the exact point of x equals 1. Okay, so again, a chord is the line that cuts through this. So we don't actually have a tangent line here. A tangent line would be one that cuts right, we're looking at it at the point 1. So a tangent line would be one that just touches right there at the point. This is a chord, or a secant line. A secant line cuts through a graph. So we're looking at a secant line, and we're going to try and get it closer to the actual point here at 1. Alright, so we plug in 1 for our x. Whoops. What is this? Let's get rid of that. Okay, so we plug in 1 for our x, and we solve for y, and we get 1. We plug in 1 for x for 1.001. We square that, we get 1.001 squared. So finding our slope, our gradient, we're going to take the y2 minus y1 over x2 minus x1, calculate that out, and we get a slope of almost 2, a little over 2. Alright, this is our good friend Isaac Newton. He's going to make an appearance, and he's going to help us along as we go a little bit further. So Isaac says that we are getting close to 2 as well. So let's see what this looks like with another example. Now we're going to go with the coordinates 8 and 8.001. So we're going to look at our graph again. We're going to take 8 and square it, and then we're going to take 8.001 and square it, and we get 64 and 8.001 squared. So we'll figure that out here in a second as we start calculating the entire slope, the entire gradient, and we get a gradient of approximately 16, a little over 16. Alright, let's take, there's Isaac again, let's take this and put it into a table. So far we've got our gradient. When x is 1, y, this is for, again, this is for y equals x squared. Whoops. Let's make that a little bit neater. Y equals x squared. So when y equals x squared, we so far have, when x is 1, the slope, or the gradient, is 2. When x is 2, the gradient at the point is 4. When x is 8, it goes to 16. So you're probably seeing a pattern, but can we actually prove this? So what we're going to do is we're going to compare Newton and Leibniz, Gottfried Leibniz. He is the other guy who was inventing or finding calculus at the same time that Newton was. So Newton says, I'm going to use h. He uses the term h for his calculations. Leibniz uses delta x. So depending on which book or which notes you're looking at, you're going to either see h or delta x. And what we're going to do is we're going to find the distance from 2 to some other value. We're going to make it really small though. We're going to make a very small distance for h. So as we do that, we're going to have our second point is going to be 2 plus whatever we have for h. So 2 plus whatever we have for h is going to be 2 plus h. Then 4, if we plug this into our calculation, we would square it. But now we're taking whatever we have for our x value here, make it a little bit easier to see, and we're squaring it. So we're taking 2 plus h and we're squaring it. We're going to look at what this formula looks like. So we've got 2 points, 2, 4, and then 2 plus h and 2 plus h squared. Right? Those are our 2 points. So now we're going to kind of come up with a general formula here. So if we make h infinitesimally small, just like we do with our limits, that it's practically the same point, but it's not that same point, we can start finding the slope at point A. So we're going to draw our chord in there, and we're going to find the gradient of AB. So we've got y2, 2 plus h squared, minus y1, which is 4, x2, 2 plus h, minus x1, 2. Simplify that, so we multiply out our 2 plus h squared. So we're going to expand that. We'll simplify a little bit. We get our 4h plus h squared divided by h. Factor out an h, simplify, and we're left with our gradient being 4 plus h. Now, h, remember, we said that's infinitesimally small, so we don't even really consider that, and our gradient as h approaches 0 is going to be 4. So the gradient of the curve at the point 2, 4 is 4. Okay, so take a second, use the same formula, but instead of 2, use 3. Instead of 3, use 4. And plug in those values to find the gradient at points 3, 9, and 4, 16. Pause the video and actually try this, so that way you can get a feel for what's happening. You can use these examples or this example that we have on the screen to help you guide through that. So hit pause and try and find the gradient at 3, 9, and 4, 16. Okay, so now we fill in our values and we're starting to see a pattern here. And our gradient, if you notice, our pattern is going to be 2 times what, whoops, sorry about that. It's going to be 2 times whatever x is. So whatever our x is, if our x is 5, then we're going to get 10. If our x is 6, we're going to get 12, 7, 14, 8, 16, and so on. So we just double what our x is. Alright, so let's look at some of these things filled in on an actual graph. So here's our first result. This is for, what value is this one? Where are we crossing? We're crossing at 9. So we're crossing at 3, 9. And at 3, 9, we have our gradient of 6. So if you count over 2, so your x is over 2, your run is 2, your rise is 1, 2, 3, 4, 5, 6, 7, 8, no, what am I doing here? Our rise is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Our run is 1, 2, yep, so we've got 12 over 2, gradient is 6. Okay, here's our next one. This is for 0.24. And if you count over your rise and your run, you're going to get your gradient at 4. And we keep going. At 1, 1, we get our slope of 2, our gradient of 2. At 0, it's going to be 0 because we don't have a slope. It's a horizontal line. But then we start going into our negatives, what's going to happen? So at negative 1, 1, now we're going to get a gradient of negative 2. And again, you can count over and up your rise and your run and double check that. And we keep going, that we keep on getting 2 times whatever x is for our gradient. All right, so let's say we want to look infinitely close, or a lot closer than what we are. So let's zoom in on this point and see if we can get even closer to that. So here we go. We're going to create our tangent line. So we've got our 2 points. So it looks like it's a straight line, but remember this is still a little bit of a curve. This is still, the red line is still the curved line. So we're going to create a tangent line there at the point. We can find our slope. We're going to do our rise over our run, 0.8 over 0.2. So if you look at your scale, we've got 0.8 over 0.2, and we still come up with a gradient at 4. So all of our slopes are coming out to 2 times x. We're going to take this a little bit further in class and see what we can come up with and expand on that.